So, we were discussing about the criteria for the convergence of sequences, and in this process we have seen two criteria. One is the monotonic convergence criteria for monotone convergence sequence, but that monotone convergence theorem, which is a very wonderful result, which gives the convergence criteria for a sequence, particular type sequence which are monotone, either monotone increasing or monotone decreasing sequence. And another criteria which is general in nature, that if a given sequence is given, one can find the limit of the sequence, and if the limit exists, we say the sequence converges. If the limit does not exist, all goes to infinity or minus infinity, we say the sequence diverges. But you see, in both the cases, there is a in the first case particularly, there is a drawback in the monotone convergence theorem. The main drawback is that this result is only applicable to those sequences which are monotonic in nature, but the sequence may not always be monotone sequence. So, in such a case, the monotone convergence theorem is not applicable to judge the convergence of the sequence. And second criteria which we told, though it is valid for any type of the sequence, but in identifying the limit itself is a problem, is a difficult one. So, what we want is, will there be any criteria which can directly say the sequence, given sequence is a convergent one or divergent one without going for the limit, and this is given by Cauchy, and it is known as the Cauchy convergence criteria, and it is one of the important result which relates the convergence of a sequence of real or complex number with its Cauchiness. So, in fact, if a sequence is Cauchy, then automatically it will be a convergent and vice versa. Now, this is valid in case of the real complex numbers, but when we go for an arbitrary metric space which we have not taken up, then the convergence criteria obviously does not help there. So, they will be defined in a different way, the convergence of a sequence. Okay. So, we will go on, since we have restricted our study only for the real number or complex number. So, therefore, this convergence criteria is very much helpful in getting the result for a nature of the sequence which is convergent or divergent. So, before going with the Cauchy convergence criteria, what is the Cauchy sequence? So, we say first definition of a Cauchy sequence of real numbers. A sequence x n x, which is x n of real numbers is said to be Cauchy sequence if for every epsilon greater than 0, for a given epsilon greater than 0, for every epsilon greater than 0, there exists a natural number or positive integer, you can say natural number, say n, which depends on epsilon, such that for all m n natural numbers m n greater than equal to capital N, which depends on epsilon of course, the sequence of the terms satisfy the following condition. These terms of the sequence x n satisfy the following criteria that mod of x n minus x m is less than epsilon null. It means a sequence is Cauchy if x 1, x 2, x n, this is a sequence of Cauchy numbers, a sequence of real number or complex number. We say this sequence is a Cauchy sequence if for every epsilon null greater than 0. So, first you choose the epsilon null, then corresponding to this epsilon null, one can identify a point x n such that when we take all the terms after this x n onward, the difference between any two arbitrary terms after x n will remain less than epsilon. The distance between x n and x m will remain less than epsilon. All it is in the epsilon neighborhood of one of the say m I fixed, then one of the point in this. So, they are very close to each other. The distance between any two arbitrary point after the certain stage capital N onward, the difference is very small or is less than the given number epsilon. If this happens, then we say the sequence is a Cauchy sequence. For example, if we look the sequence, say x n is say 1 by n, we claim that the sequence 1 by n is a Cauchy sequence. So, it means for any epsilon null is greater than 0. So, because if we choose any epsilon null, because let us pick up choose any epsilon null greater than 0 first, then corresponding to this epsilon null one can find a natural number, then corresponding to this epsilon null to this epsilon null greater than 0, one can find a natural number say capital H, which depends on epsilon null such that let us say H is such which is greater than 2 by epsilon null. So, H will depend on epsilon null, we can choose a natural number which is greater than 2 by epsilon null. Then according to the Cauchy definition, this difference must be less than epsilon null. Okay. So, if I choose m n greater than n, so if we take n and m a natural numbers which is greater than equal to h, we have 1 by n is less than 1 by h, okay, or less than equal to 1 by h, and but h is greater than this. So, it is less than epsilon null by 2. Similarly, 1 by m is also similarly 1 by m, which is also less than equal to 1 by h. So, it is strictly less than epsilon null by 2. So, these two are less than epsilon. Therefore, when we take the difference between mod of x, therefore, mod of x n minus x m when n m are greater than h, this is nothing but the 1 by n minus 1 by m, and by triangular inequality it is nothing less than equal to 1 by n plus 1 by m, but 1 by n is less than epsilon null by 2 and 1 by m is also less than epsilon null by 2. So, this is less than epsilon null for all n m greater than equal to h. It means the difference between two arbitrary term of the sequence after this certain stage h onward is less than epsilon null. So, sequence 1 by n is a Cauchy sequence. Okay. That is one. Now, what is the negation of the Cauchy sequence? The negation of, because that will be required, negation of Cauchy sequence. If a Cauchy sequence does not satisfy, if a sequence x n does not satisfy the Cauchyness. So, what is the negation of Cauchy? Negation of the definition of Cauchy sequence. Negation of definition of Cauchy sequence. Sorry, definition of Cauchy sequence. The negation is like this. The Cauchy sequence says that for every epsilon null greater than 0. So, negation will be there exists an epsilon naught, and this should there exists a natural number So, we can say that for every natural number h, then for all natural number h, so there will be a natural number m and n which are greater than h and satisfy this condition. Okay. So, we can say the negation like this: there exists epsilon naught greater than 0, a small number epsilon naught greater than 0, such that for every natural number h, there exists for every natural number a, there exists say at least one n which is greater than h and 1 m at least 1 m which is also greater than h, such that the difference between the terms of the sequence x n and x m is greater than equal to epsilon naught. Okay. Then this will be a negation of the definition of Cauchy sequence. It means, if you want to show the sequence is not Cauchy, then this criteria must be satisfied. For example, if we take this sequence, say x n is the sequence like 1 plus minus 1 to the power n, this sequence. So, then we claim that the sequence x n is not Cauchy. This is our claim. It means this condition is not satisfied. So, let us pick up the epsilon naught. Okay. So, let us choose epsilon naught equal to 2. There exists an epsilon naught, we take epsilon naught. Then, since the sequence x n is such which goes to 2 if n is even and goes to 0 if n is odd. So, if we take the n as even and n plus 1 becomes odd. So, difference between these two will be 2, which is epsilon naught. So, in fact, then for any h natural number h, we can choose an even number n greater than h, and then m, let m is n plus 1, which is also greater than h. We get mod of x n minus x m is nothing but what? When n is even, the x n comes out to 2, and when m, which is n plus 1 odd, so it is 0, which is exactly same as epsilon naught. So, this satisfies the convergence negation of the definition of Cauchy sequence. Therefore, sequence x n 1 plus minus 1 to the power n, this sequence is not Cauchy. Okay. So, the significance of the Cauchy sequence is the significance of Cauchy sequence lies in the assertion, lies in the main theorem, in the assertion. The assertion is that a sequence is Cauchy, a sequence of real number x n of real numbers is Cauchy if and only if it is convergent. If and only if it is convergent. So, that is the main item. that if a sequence is Cauchy, then it has to be convergent, and if a sequence of real number is convergent, then it will be Cauchy. So, this is the main result which we will show it here, and that is why the definition of the Cauchy or Cauchy sequence plays the vital role in the set of real numbers, system of the real numbers. Okay. Let us see the first lemma, which he says, which is used, say lemma 1. Okay. If x, which is x n, is a convergent sequence, of real numbers, then the sequence x is Cauchy, is a Cauchy sequence. So, this is the first result which we want to show, that every convergent sequence is a Cauchy sequence. The proof of this is very simple. Suppose limit of the x n as n is x, because it is a convergent sequence. So, limit will exist, and suppose this limit is x. Then by definition of the limit for given epsilon greater than 0, there is a natural number say n 1, which depends on say epsilon 2, such that if we take n greater than equal to n 1 depends on epsilon 2, then mod of x n minus x is less than epsilon by 2, let it be 1. Okay. Now, if we take if we take another number n 2, we take n 2 which is greater than or equal to say n 1 depending on say epsilon 2, and if we choose n and m greater than or equal to n 2, then obviously for this particular n 2 this result is also valid, because this is true for all n greater than n 1. So, if we take n which is greater than n 2, that will also be satisfied, because it is greater than n 1. So, it will be satisfied. Then we have mod of x n minus x m, apply the time this is less than equal to x n minus x plus x m minus x. Now, this is less than epsilon by 2, this is less than epsilon by 2 for all n m, greater than n 2. Then in that case, the difference between x n minus x m is less than epsilon. So, this shows that, but epsilon is arbitrary, any number we can choose. Therefore, it follows that the sequence x n is a Cauchy sequence, is a Cauchy sequence. So, that is what we wanted to prove. Okay. Okay. Now, as we have seen that a convergent sequence is a bounded sequence, and we have seen that every convergent sequence is a Cauchy sequence. So, basically that we are going to show this also, that every Cauchy sequence is also bounded sequence. Okay. So, that will the next result is lemma 2 says that a Cauchy sequence of real numbers of real numbers is bounded. So, the proof is just based on the similar lines as we have done it in case of real. So, what we do is we take the sequence x n, which is a Cauchy sequence. Since Cauchy criteria is satisfied, so applying the Cauchy criteria, you can date the sequence x n is dominated by a certain number after a certain stage, and for the remaining one finite sum, take the maximum value. So, that is what. So, let x be a proof. Let us see the proof is. So, let our sequence x, which is x n, is a Cauchy sequence of real numbers. So, by definition, for epsilon, any epsilon greater than 0. So, if we take epsilon, let epsilon is equal to 1. So, corresponding to this epsilon, there exists a natural number. This is sign for there exists natural number h, which depends on epsilon. Epsilon means 1, such that for all n greater than equal to h, the difference between x n minus x h is less than 1, because m we can choose. So, m is h. So, anyway, this implies that the sequence x n is less than 1 plus mod x h for all n greater than or equal to h. By modulus, because if this is greater, then we can just take it, or less than greater than equal to mod x n, and then. So, basically this is mod x n. Mod x n is less than this. Okay. Let it be 1. And then further you choose capital M as the maximum value or supremum value of mod x 1, mod x 2, mod x h minus 1, and then 1 plus mod x h. We can also use the maximum. In fact, supremum I have not defined, because these are finite number. So, we can change this by a maximum also, maximum term instead of supremum, that is okay. We can also take this maximum. So, when you take the maximum of these two, suppose m, then what happens? All the terms of the sequence x n will be dominated by m, and this is true for all n. So, this shows the sequence x n, this sequence is a bounded sequence. Bounded sequence of real numbers. So, every Cauchy sequence of real number is bounded. Let us see the converse part, and converse part will prove the Cauchy convergence criteria, that is complete. So, what the lemma 3 says, lemma 3, or you can say every Cauchy sequence, every Cauchy sequence of real number every Cauchy sequence of real number is convergent. So, combining first and second, Cauchy sequence of real number is bounded, and Cauchy sequence of the real number is already we have seen a convergence sequence real number is Cauchy, and if we prove the Cauchy sequence, every Cauchy sequence is convergent, then we can go for the Cauchy convergence criteria. Okay. So, let us see the proof of it. Suppose we have a sequence x, which is x n, is a Cauchy sequence, let be a Cauchy sequence of real numbers, Okay. Now, this Cauchy sequence by previous result a Cauchy sequence of real number is bounded by lemma 2. If you see, every Cauchy sequence of real number is bounded. So, by lemma 2 it is a bounded sequence. So, by lemma 2 it is a bounded sequence of real numbers. And by Bolzano-Restas theorem says, if a sequence is bounded, then it must have a convergence subsequence. So, by Bolzano-Restas theorem, by Bolzano-Restas theorem says that there is a subsequence x dash, say equal to x n k, x suffix n k of x that by Bolzano there is a subsequence x that converges to the some real number x star. Real number x star, some real number x star. Now, if I prove that our sequence x n also converges to the same number x star, then result is complete. So, what is required to prove is that the sequence x n will also converge to x star. This is our problem to solve. Okay. So, let us see how to. Now, what is given? The sequence x n is a Cauchy sequence. This is given. So, since sequence x n is a Cauchy sequence, so by definition of Cauchiness, for given epsilon greater than 0, there is a natural number say n 1 depends on epsilon such that for all n and m greater than or equal to n 1, say epsilon by 2. Let us take the epsilon by 2, because we will need further epsilon by 2 n 1. We have such that for we have the difference between x n minus x m is less than epsilon 1. Let it be 1. Okay. Now, the subsequence x n k is a convergent subsequence, converges to x star. So, by definition, again apply the definition of convergence sequence, which has a limit x star. It means limit of x n k when k tends to infinity is nothing but x star. So, since the limit of this x n k when k tends to infinity is given to be x star. Okay. This is given, we have got it, is it not? So, by definition of the limit, we can say for given for the same epsilon, for epsilon greater than 0, which is the same epsilon, there exists there is a natural number, say n 2, which is suppose greater than or equal to n 1, which depends on epsilon by 2, such that n 2 and such that this n 2 where n 2 greater such that this n 2 belongs to this set n 1, n 2, n etcetera. This set means we are choosing the positive integer from a sequence n k's. So, there exists a natural number n 2 from this set, which is greater than equal to n 1, such that mod of x n2 minus x star is less than epsilon by 2, because this is difference of this can be made as small as we please. So, when k is sufficiently large, it goes. So, we can choose the n 2 which is in this case greater than n 1. So, that this condition is satisfied. Second. Okay. Now, consider, and this is true for what? This is okay, this less than s. Now, further this n 2 is greater than equal to n 1, which depends on epsilon by 2. So, from 1 the result is also valid when you replace m by n 2. So, from 1 we can say the result mod of x n 2 minus x n is less than epsilon by 2 for all n greater than n 2 depends on epsilon by 2, okay, for all n, because m I can choose to be n 2. Now, consider mod of x n minus x star. Now, this is less than equal to mod of x n minus x n 2 plus mod of x n 2 minus x star, and then this will remain less than epsilon by 2 plus epsilon by 2 for all n which are greater than or equal to n 2 depends on epsilon by 2, because both the conditions 1 and 2 are satisfied by this. So, what is that? The limit of x n is also n, limit of x n and n tends to infinity is also x star. This shows the Cauchy sequence is convergent, because epsilon is arbitrary. Since epsilon is arbitrary, so once it is arbitrary, we say limit of this. Okay. Therefore, the sequence x n which is x is convergent. Now, this lemma 1 and lemma 2 and 3, if we combine this 1 and 3, if we combine, we get the result which is known as the Cauchy convergence criteria. Cauchy convergence criteria, and that is very important result. What this criteria says? A sequence of real numbers is convergent if and only if it is Cauchy sequence. It is a Cauchy sequence. Okay, and this proves the result. So, combined